All right, so most of you submitted a submission. I believe 25 of the 29 had a group, and I think 2 or 3 submitted individual submissions. So I'm going to go through and try to put groups together, and I'm going to use a random number generator. If I, for some reason, hook you up with somebody you have a blood feud with or something like that, please let me know. I would like to get ahead of that before you guys try to kill each other. And then, so basically, I also added this thing, creativity challenge. This is something I'm trying new this semester. Usually I get, please turn in your assignments, Michael and Olivia. So basically, Michael, Olivia, Michael, Olivia. All right, good. So, by and large, students react very well to topical guide objectives. I do get the occasional student who just feels like they're just blindly copying notes. Now, what I'm proposing is I'm going to try to have a weekly and annually a weekly creativity challenge that will require you to combine a number of concepts from the homework assignment that week. The goal is to provide you with an extra credit opportunity. For example, let's say you submitted a creativity challenge and if you can get up to 10 points. If you get 6 of them, that's 6 extra credit points. You still need a total, and those extra credit points go towards your TGO score. You still need a 70% average on the TGOs in order to pass. If you have less than a 70, I will give you a D, regardless of how well you did on the exam, as it says in the syllabus. But you can use this if you're the type of person who feels like my creativity juices are flowing, I really get this material, and the topical guide objectives bore me. This is another avenue for you to show me that you have the knowledge in your head. So the creativity challenges and the projects are going to kind of follow the same format. So I wanted all of your groups to kind of give an honest attempt at writing up a basic project description. I'm going to go into more detail of what I expect from you for the rest of the semester. That's why I called it Project Zero, so it's kind of a learning experience. You're going to put your group name. For those of you who probably saw, I've been putting in your groups on Blackboard. Putting in the group name allows me to quickly find your groups. I can put in your grade. Putting your, so here I've called my group, which is myself. I call it the Gregarious Professor. You're going to put your group members here. And then you're going to put group contact email. I recommend rotating for each, have somebody different. This is an email that I'm going to send if I need to send some sort of small, quick message to kind of poke somebody. Like, hey, I need you really quickly. You're missing a file. Please submit it. And then that person will follow up. If it's something serious, I will contact all of you. But this is just the quick message. Honor statement. All of your projects will include this honor statement. Now for me, I pledge my honor. I have not cheated, nor will I cheat on this coding assignment. So I have a little spiel here about using common sense. Don't just copy and paste. You are a group of people. You are not I. You are not the Queen of England. You may not. So I want you to say, we pledge our honor. Use proper pronouns. Also, I've shown this as an exam on the past, so people have said I've not been cheated on this exam. Well, this is a coding assignment, not an exam. So, historical research. Now, for each project submission, I'm going to give you 2 innovators in computer engineering, and I want you to kind of write a 2 to 3 sentence background on each of them, and you're going to include that on your cover page. So, for the example here, I've chosen David Patterson and Dennis Ritchie. I want these to just be in your own words. I kind of want you to kind of get an understanding of some of the people who have innovated your work. So David Patterson is one of the authors of the course textbook. He was the innovator of reduced instruction set computer, RISC, which you now know about, and he also led the development of MIPS. So all of you who are familiar with RAID, redundant arrays or independent disks, is now redundant arrays of inexpensive disks. He also invented that, and he's now the department chair at Cal Berkeley. And I've also included Dennis Ritchie, who invented C programming language, and he's also is the Unix operating system author of the fundamental textbook, The Designs of Switching Circuits, and the C programming language. For the rest of your project, should be Times New Roman 12-point font with 1-inch margins, double spaced. Pseudocode and headers and copied output, you should be single spaced, and I give examples of the difference here. So, table of contents, project description. I'll show you a project description. Project design. Project description, you're gonna basically parrot back to me what the project description is, but you're also gonna show me how you're kind of making observations about things I wrote, things I didn't write. Project design, design choices and pseudocode for your project. Here I have page 5, library map and function calls. Page 7, challenges, and page 9, output results. So page 1, I asked you guys to write a program that implemented this melee machine. For each state, we're required to have a function call that is then called by main. We're also required to implement 7 iterations of the FSM. Example 2 had said 7 iterations, so we may use that as our test case. So I'd copy and paste it here. The input array is 1, 0, 0. We know from lecture that the output is 0, 1, 0, 1, 1, 0, 0. And I said screen capture from the video, and there it is. Dr. Morrison did not require that we store the FSM outputs, so I decided to print the results to the screen. Therefore, we can reduce the number of preconditions and postconditions by only passing the input to the state function and returning the next state. By implementing the required switch statements in main, we accomplish the project in the following manner. So project design, here you're going to talk about specifically the flow of your design. So here I talk about what the design is. I should note that I've posted this as well as my solution for the creativity challenge on Blackboard. It became available at 9:30 under C programming assignments. So this PDF document is available to you as well as that code. So here I first wrote the main pseudocode. So I wrote iterations. The current iterator is at 0, current state, and an input array. While cur is less than iteration, so it's going to increment cur, and then it's going to go through each switch state. So here, if it's case 0, it's going to return the next state, and then it's going to go again and find the next state, and so on, right? And so this should say state 2. And then from there, I wrote pseudocode out for each state, print 0 and return 2, print 0 and return 1, and so forth for each one, because that corresponds directly to the finite state machine here. And then implemented our header files. Library map, this is single space because this is a little note I've given to you. You need to include a library map I've described in class. Here I had fsm states.h. In that file I called sstudio standard I out. Standard lib I called in immediately FSM because in my switch statement I included standard error, which I sent as a message. I didn't require that for your coursework, but for the assignment, but I wanted to include that as an example. Function call, standard lib, I called main, called in main for standard error, assignment, standard IO. You want to start keeping track of all of these. And so then I actually copy and paste the .h function declarations. Right? And so challenges. So here I actually to document the challenges you encountered. For example, you spend 8 hours on an error, and you find out that it just requires like saving your file in a different spot. I want you guys to be thorough. So this is the point. Project is due in 2 hours. My code doesn't work, or it is not giving me the output results I want to do. So this is where you encounter, your adversity, right? So a lot of people counter it in 3 ways. You get frustrated, you get intimidated, and you get motivated, right? So if you get frustrated and intimidated, that's where the temptation to go on Google, find some code, put it on there, right? Cheat. Or you can use your challenges section to try to thoroughly describe why it is your code doesn't work. I don't necessarily need you to turn in perfectly working code. What I want you to show me is that you have knowledge. The code doesn't work, and you can go through and we tried this, it doesn't work because of this, it doesn't work because of that. I will give you a decent amount of partial credit. But I want it to be your own work. If you show me this, I can go through your code and show you where to fix your errors. So that way, when you build on it for the next portion of the project, you can learn from that. And that's why, if you noticed in the syllabus, the project points grow throughout the course of the semester. That's because I want you to make the mistakes early on in the semester on lower point projects, and then as you learn from it and you start doing it better in the higher point projects, you'll gain the higher points because you won't make those same mistakes. So the challenges section is specifically for that situation for you to document what it is that you don't understand. And so if I'm going through all 9 or 10 projects and I see all 10 groups or 8 of the 10 groups had the same challenge, well, that's something I can change in the project description, right? That's something that's feedback to the professor. So this is, don't succumb to adversity. Get motivated, go through, type it out. And sometimes if you type it out and you try to, students have found this, if you try to explain to me what your problem is, you'll find out what your problem is. And then you just put in there, and then we figured it out by doing this, and then you have a really nice challenges section and working code too. So here, I sent out this email yesterday. I realized I could have been more clear on how you can initialize an array of 5. I sent an email to class. It relates to 1.1. So the email I sent to you was that more FSM example. So you saw how to do it, but you still had to actually correlate it properly to the Mealy FSM example in 1.2. I had not mentioned stdr in class, so I mentioned standard error. You can use fprintf stderr, and then from there you're able to it prints it to the error IO port. That's why I said you can pound include standard library. We're going to be going over that much more in sections 3 and 4. Additionally, I realized I had one time where I got a compiler message where I had all of these error messages, and the result was from one bad put in standard IO.h. I inadvertently put this character right behind it, and it caused 20 errors. The reason I wanted to show you this in class is because for those of you who are new at coding, when that comes up and suddenly you get 30 error messages and you think you only put in one line of code, how in the heck did that happen? Go to the first line and correct that first. And then a lot of times, many of the error messages will go away. And that's what happened there. I got rid of this and it all went away. And so I said that I'd inadvertently included a character here. While I'm experienced enough in coding to recognize a stream of error messages from a compiler is caused by a single error, this may be intimidating to new coders. So I will introduce this into the new lecture and then update section 2 for future courses to try to get ahead of this issue. And so compiler and output results, I want you to copy and paste to show that it works. So, for those of you who are using Eclipse CDT, which appears to be almost all of you, you get this build message, right? I want you to copy and paste that, show me it worked, and then copy and paste your output. So if you go on Blackboard, right? See if it actually does. Yep. And then, because I changed my password, no. And now what you want to be able to do is you're going to be able to go under Content, and then C Programming Assignments, and then is now available Project Submission Example, and it's a little zip file. And as you'll see, let me go back here because that's not. Downloads. Fortunately, I don't have anything awkward on here.
It's a work computer. I better not, right? All right. Well, it has. That's taking too long. All right. So basically, it has the PDF that I just showed you and my I have my two .c files and my header file that shows my solution to the creativity challenge. So creativity challenges, I'll try to come up with at least one per week. If you may propose a creativity challenge if you so desire. If you're going over something in class, like, it'd be really interesting. Try to figure this out, and I'll try to take what you proposed and make it appropriate for the class, and then I'll put them out every Thursday, and they could be due on Tuesday. So they'll give you an opportunity to do some extra credit, and if you do like 2 or 3 of them, right? If you have like a exam, the theory that all the professors, we get in our black hoods and we get together and we put all of our exams on the exact same dates, right? Totally not true. No. There's just, because of the way the calendar works, it just becomes appropriate dates. But if you do like 2 or 3 of these and you're like, I just want to take a couple days off from the TGOs, well, you've earned them by earning extra credit. So, does anybody have any questions about this before we move on to lecture?
So the write-up,
yeah.
Is the write-up also for project assignment?
Yes. Yes. The project description write-ups will be more in depth, obviously, because of their what's required. But the creativity challenge, I know it's 10 pages, but you saw the overwhelming majority of that was annotations and do this and don't do that. So it'll probably be something like 4 pages or so, which turns out to be fair because of how much you guys are submitting here. I've just put this together so that way, Tony, I'm not losing your front page of your assignment. All right, so any other questions? Okay, so we've now covered the basics of C coding. We're going to be learning C coding along with the material as we go along. So we're going to be covering arithmetic. We're going to be going a lot to pointers in section 3 and more detail about function calls. And as we go along, I'm going to teach in section 4. We're going to be learning about memory, so you'll learn about structs and how to call structs and pointers and that kind of material. So, and then everything will come together as you start seeing C to MIPS compilation. You'll see what's physically going on when you write your code, and hopefully that by understanding that'll actually make it much easier for you to be able to actually implement your assignments. Let me turn Epic Pen on here. All right, so I started this section. I have this quote from Thomas Hobbes. I'm sure you all, now I might be dating myself. How many of you are familiar with Calvin and Hobbes, the comic? So, okay, so a decent number of you, so I'm not that old. Good. All right. So Thomas Hobbes, the philosopher in 1856, also talked about computation. He said, now to compute is either to collect the sum of many things when they are added together, or to know what remains when one thing is taken from another. And if any man adds multiplication and division, I will not be against it, seeing multiplication is nothing but addition of equals one to another, and division is nothing subtraction of equals one from another. So multiplication, you're just, 6 times 5, you're just adding 5 6 times, or 6 5 times, and division, you're basically 18 divided by 5, you're just subtracting 5 from 18 3 times, and you get a remainder of 3. So the ratio summation is comprehended in these 2 operations of addition and subtraction. Now, why do you think this would be an important quote to include in the context of what we've learned so far, specifically the type of architecture that we're using?
It takes complex logic and simplifies.
Mm-hmm. And what are you trying to do in the architecture?
Make it run faster.
Make it run faster. And so the design choice for MIPS, what is simple? I'm looking for one specific word that starts with an R. Yes, reduced instruction set computer, right? So basically, Thomas Hobbes in 1656 is talking about the basic concepts that eventually became a reduced instruction set computer, right? We can say we can either add this multiplier or divider. Now you'll learn about multiplication and division algorithms in this section. But you can just simply use shifters and adders to be able to accomplish this more efficiently. So what goes on inside an arithmetic logic unit? So this is the basic idea of what's in an ALU. So you have your control unit, sending values to your arithmetic logic unit, and then you have register inputs. And then inside this magical box, you're doing some sort of arithmetic operation. For example, machine instruction, add T1, S1, T2. So this is assembly language, and what this means is you're going to add S1 and S2. This is $S1 and $S2 are notation for registers. You're going to add their sum. You see how this result is put into another register? That result is put into register T1. And so you have some sort of flag. We're going to talk about overflow flags and carry out. Items like that. So the general idea is that you want to be able to control what's going inside the ALU using this controller. The registers are your inputs that you're going to be performing operations on, and then you're going to get the outputs. So MIPS uses 32 bits for everything. Remember in the RISC versus CISC, we talked about how RISC is fixed instruction lengths and CISC has a variable instruction lengths. So everything for MIPS is 32. Now, TGO 3.1 is the representation of the extreme positive and negative numbers. So if you have a 0 and then 31 ones, it equals 2 to the 31 minus 1. And then a 1, and then all zeros, it becomes negative 2 to the 31. And so what we're going to be talking about here is that this first bit is the sign bit. And as we're going to talk about down here in a second, MIPS uses 2's complement. Which, since you guys have all passed regular digital systems, you know, correct? General idea? All right. So, but we're going to be going over an example here in a second. So, you can simplify it. You say 0, 1, 1, 1, 1, 31 bits. Or you can go 1, 0, 0, 0, 0, dot, dot. And then you can say 31 bits. When we get an IEEE 754, this being able to summarize that's going to become very useful. Save you some writing. Yes?
1, 0, 0, 0, 0. Wouldn't it be like minus and 0? The actual number you're putting there is 0. But
no.
You have your minus sign.
This is that is a gross conceptual error. So these significant bit, remember we're using 2's complement. Right? So what is the 2's complement of this number? Yeah, so that's why. Any other questions on this? All right, so let me scroll up a little here. So, and then I'm just indicating the honors in MIPS, the most significant bit, MSB. MIPS is used to represent the sign of the number. And so by writing that down, we can give a little description and kind of follow up on your question here. Subtracting 6 from 7 in MIPS. You do the same thing when you basically take the 2's complement and add. And we're going to discuss how this is physically done a little later. So you take the 2's complement, everything goes to 1. And this becomes 1, 0, 1, 0. And the reason why is 6 is this, right? Then take the 2's complement, and it becomes 1, 0, 1, 0. And then what happens is you add them together, and you're going to get 1, 0. You get a carry here, it's going to be 0. Carry here, 0, and so on. So then 7 minus 6 just becomes 1. So So we're going to differentiate between overflows and exceptions. So overflow, you're going to have an overflow bit as one of your outputs, right? That diagram I just showed you where they had like flags. One of them is going to be overflow. Overflow occurs when the result from an operation cannot be represented with the available hardware. So that's why, let's say I wanted to add, remember we have 2 to the 32 minus 1, right? So let's say I want to add 5 to that. So that's our maximum. So this becomes all ones, right? And then I want to add 1, 0, 1. Well, here's what's going to happen. You get 0, 0, 1, 0, and so forth. And then the most significant bit is going to change because it's going to continue to overflow, right? That is how that's where our definition of TGO 3.3 comes into play, because that most significant bit by flipping now changes this. So now it's going to be 1, and all over here we have 0, 1, 0, right? So now we would take the 2's complement, and instead of this number being 2, it now becomes 1, 1, 1, 1, 1. So almost 2 to the negative 31, right? 2 to the negative 31 minus 1. So I kind of described when can overflow occur. So you're adding operands with different signs. So if you're doing 6 plus negative 7, right? You can't have it occur because there's no scenario in which you can exceed one of the 2 maximums. The only way you can exceed the 2 maximums is if you have a positive number that can take a positive number over the positive maximum, or if you take the negative number and subtract it to get past the negative maximum to create that overflow, which would then change the sign. Okay. So again, subtract 1 from 2 to the 31 minus 1 for MIPS, and this is an example here of overflow. I've subtracted 1, and it gave us 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. So now it's representing positive 2 to the 32 minus 2 instead of, so now that should be negative. I'm sorry. Yeah. So if you're subtracting 2 positives, it's not going to overflow. That's what I meant here. So if you're subtracting 2 from the same or you're adding different numbers, you cannot get overflow, but here you can. And here I show an example. Let me move this up just a little more so everybody can see. Here I add 1 to 2 to the 30 to the negative 2 to the 31 minus 1, and it then becomes negative 2 to the 31. So I think in section 4 I include a funny video game story where I think the game was called Civilization, but the whole idea about it was that you were able to choose somebody in history and have them try to become the leader of the world. And everybody had different measurements, and they used unsigned integers to represent the leader's aggression. And so Gandhi, they put him as 1, and so it was an 8-bit architecture, so you could have it from 0 to 255. So they had Gandhi as 1, as the probably represent the probably least aggressive person. Now, as part of the game, if you became a democracy, you got 2 subtracted from your aggression score. So 1 minus 2 was supposed to be negative 1, right? But it's an unsigned integer, so guess what happened? Gandhi became an aggression of 254 and then starts dropping nuclear weapons all over the place. And it's in section 4 of this great picture of Gandhi. You're like, we are going to negotiate with nuclear weapons. And so that's what happens when you don't pay attention to how you have your compiler-driven encoding of the micro engine. So how do you deal with these kinds of things with overflow? You're going to deal with something called an exception. An exception is an unscheduled event that disrupts program flow. So these becomes an important, let's say you have an instance where you're adding, you have 2 to the 31 minus 1, and you add 20, right? So now you have some sort of overflow. The reason why you have to have an unscheduled event that disrupts program flow is because if the computer cannot represent the number in the way in which you've described, it has to stop and it has to talk to the operating system and say, hey, this number is too big for conventional format. And I'm throwing an exception. You need to do something about it. And so add immediate, and subtraction. Oh yeah, so that's So all these that we just discussed. We'll talk about this later. This exception program counter. But basically, what you want to do is you're going to store the exact instruction where the error occurred, and then you're going to be able to fix that, right? So operating system fixes error, starts it back up at the instruction, loads up all the variables that need to be fixed, and then takes care of it. And so this is kind of a note, but this is basically the name of the instruction. For those, I don't know if any of you kind of gone on and looked at the MIP screen sheet at all, but these are you'll recognize this notation soon enough when we start getting into machines and assembly instructions. So this is a register. Destination register is going to be equal to the register in which we're going to store it. So the RS is one of the 3 registers and stores it in our exception register. Okay, so the question now becomes, I want to represent a number in MIPS using something bigger than 2 to the 31 for some reason. Okay. How would I do that? I've alluded to it a bit in C coding. Remember when we had our error? I represented a float as, and put it back as an integer, and we got this huge number. Remember that? So why did that happen? Yeah, some sort of different formatting, right? I alluded to it. Well, now we're about to learn what that formatting is. That formatting is called IEEE 754 format. So that's TGO 3.5. And so now we can essentially represent from, we have negative infinity and positive infinity represented here. But basically you have the first bit is your sign bit. The next 8 bits represent the exponent. And what that means is you can represent numbers from 0 to 255 using an 8-bit binary value. So the equation here, this is why it becomes important, this E exponent becomes this value minus 127. And the reason why is because if you have, let's say you have a 0 there, now you can represent the entire range of scientific notation. You can have 2 to the negative 127. So you can represent very, very, very small numbers, or you can represent very, very, very large numbers. So you can represent 2 to the negative 127 all the way up through 2 to 128. And the reason why it's 128 is because it's 255 minus 127. So 0 for positive, 1 for negative. Next 8 bits are the mantissa. I'm sorry, the next 8 bits are the exponent, and then the next 23 bits are what is known as the mantissa. So if we look at our equation here, the mantissa is these 23 bits, right? Now what this means is 1 plus the mantissa. This becomes 1 point some sort of number, right? So if I gave you 0, 5, 6, 7, 8, and then 1, 0, 1, 0, and then 23 bits. So what is this number actually representing? So we use our equation. What is this number in binary? So this is 2 to the 0 plus 2 to the 7.
I heard it. Bingo. That's exactly right. How did explain to the class how you got 129?
2 to the 7 plus 2 to the other exponents until it goes to the
Exactly. So it's 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3. So 2 to the 7 is 128, and 2 to the 0 is 1. So 128 plus 1 is 129. So now we get 129 minus 127. So this is 2 to the 2. So that's our part of our equation. Sign bit is 0, so that means S is 0 here. So that means it's negative 1 to the 0 power. And what is any number to the 0 power? 1. So this becomes positive. So now we have our positive 1 times 2 to the 2, and it was 1010 with the first 4 bits of the mantissa. So that 1 plus the mantissa means this is 1.1010 base 2. And so what is this number? How do you figure out decimals in binary? So if we did this,
half, fourth, or one.
exactly. You guys are all hitting on it, right? 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4, and so on, right? So 2 to the negative 1 is 1/2. 2 to the negative 3 is 1/8, right? So this becomes 0.5 plus 0.125. So 0.25, 0.12, yeah, that's right. And then it becomes 0.625. So this becomes positive 1.625 times 2 to the 2, which is 1.625 times 4. So you see how you can use that to represent the same thing. If we had this as 1, 1, 1, 1, 1, 1, 1, 0, this becomes 254 minus 127. And remember we said the range is up to 120. You have a question?
No.
Okay. This represents a 120, so this becomes 127 itself. So that using the exact same number, this would just be 1.625 times 2 to the 127. Same thing if that were all zeros, this would be negative 127, right? This is all 0, 0, 0, 0. So you can see we can represent a much wider range of numbers using the IEEE 754 format. So therefore, if you had a float where you put it in as, you know, all of 3, 4, 5, 6, 7, 8, and then you had all the way down, some sort of very the second smallest number you can get without it being, so you have negative 127 times 1 point, right, 1, right? And you say, you call that as an int, right? You say %d instead of %f, what's going to happen? Yeah, exactly right. It's going to say 1. So that's why you get those weird numbers when you don't do float and integer right in printf. That's where the I/O comes into play. So I think, yeah, so I have 2 questions here. We're going to do the exact same thing. Let me get rid of A here and B. All right, so I want you guys to tell me what these numbers are using your IEEE 754 format. So A could be 1, then 8 ones, and then 23 zeros. What is that number? Negative infinity, correct. So what is that number? Let me ask this in another way. What is that number in the IEEE 754 format? Put it in the equation.
So what's the simplest part of the equation? Yep, there you go. No one ever gets that wrong, right? So it's -1 to the s, and that's what's this one? So it's going to be -1 times, what's my mantissa?
0.
And then what does that become in the equation? 1 plus 0, right? Times to the what?
Factorial.
8.
2 because it's 1 or 2 to the 8 plus.
I mean summation. That's I see what you meant. So what is this number in binary? If 255, right? So if it's got 2 to the 8, it's going to be 256, right? So that would be if we added one more 1 and did a bunch of zeros. So this becomes 255 minus 127. So that becomes just negative some huge number. 255 minus 127, which goes 2 to the 128. And if you just change the sign bit, then it becomes positive 2 to the 128, right? So let's do part 2. So here we have a binary number. What's the easiest part? Yep, -1 times 0, right? So what's next? What's the next part of the equation? So this is, for those of you who can't see in the back, this is an 8-bit number. 1 is the first one. That's 2, you've got 2 to the 7, and then you got 2 to the 2, and then 2 to the 0. That's 128 plus 4, 132, 133. So whoever said over there is correct. Leo, right? Yeah. Leo is correct. So this becomes 133 minus 127, right? So that becomes what? 2 to the 6. And so what's our last part? Yes, this is 0, 1, 0, 1, right? 0, 1, 0, 1. And so what is 1.0101 in binary? What's 2 to the -1 times 0? What's 2 to the -2 times 1? 1/4, which is 0.25, right? So first part is 0.25. This one becomes 1 plus 0.25. And so what's 2 to the -3 times 0? And what's 2 to the -4 times 1? 0.0625, right? So this becomes 1 plus 0.3125 times 2 to the 6, which I can tell you is 84. And you guys solved the problem correctly. Good job. Okay, so does anybody have any questions about that? Okay. One thing on an exam, I will, these calculations, I do expect you to be able to do them here. You should, if you're a computer engineer or electrical engineer, and I ask you what's the exponent of anything between 2 to the -4 and 2 to the 10, you should be able to say it right off like that, right? So it's 2 to the 8. Let's 2 to the 9 then. Let's 2 to the 10. 1024, right? And so what's 2 to the -4?
116.
Yeah, 116 or 0.0625, right? So you saw we were able to do that. Like, make sure that when 2 to the negative 1 is 0.5. 2 to the negative 2 is 0.25. 2 to the negative 3 is 0.125. 2 to the negative 4 is 0.0625. And you'll be able to add those up pretty quick. Okay. So, as I kind of alluded to, remember we got this weird number here when we did float d as int. I put in 5.1. And then I tried printing it out as an integer. I got 1610612,736. So now we can find out exactly what happened. This is where a compiler, now that we know IEEE 754, we can actually discuss it. So you put in this number and we get this binary value. And it's 31 bits. So turns out it's 0, 1, 1, 7, 8, and then a bunch of zeros. So what is this number in IEEE 754? Using your equation. What's 2 to the 7? What's 2 to the 6? $192, right? So this becomes 2 to the 192 minus 127, which when you take care of that, it actually comes out exactly to that. So here's what happened. Your compiler saw you were trying to put a float into an integer. And so what it did was it said, that's stupid. I'm going to give you this error message. It represents this physical value. So that's why when we did the next thing, we were able to print it out and say, okay, give me 5.1 float percent 3D. It still gave me 5.10. That means your I/O said, oh wait, you're trying to send an integer out to my screen here. That's not acceptable because that's not IEEE 754, right? I'm going to give you this error message. So that's where compiler-driven encoding and microengine, operating system, and I/O turn into play. So now do you see what's physically going on underneath and why you're getting the error message that you're getting? Make sense? Good. All right, so now that we do that, let's talk about addition. I'm sure all of you are familiar with 1-bit full adders, but let's go into it into more detail. So you have your logic circuit. We know that sum is equal to A XOR B XOR Cn. So XOR and XOR, so you get A, B, and then you get Cn over here, right? And that's your output. So in the previous section, again, you have and or. In section 2, your coding assignments involve gates, right? So you have all of these gates available. So when you build a full adder, you can actually simply use those gates to be able to build your full adder, since you already have the switch statement, and it'll execute perfectly. And I'll show you an example of how that's done. So the carry out, scroll up just a little bit. Your carry out is A XOR B, so you can see if your A XOR B output also goes to AND here. And then that becomes AND C, carry in. And that output becomes ORed with A and B. Make sense? And so here your sum is going to be 0, 1, 1, 0, 1, 0, 0, 1. And it's going to be 0, 0, 0, 1, 0, 1, 1, 1. So that's your sum and carry out values, truth table. So from what you know about functions right now from this class, if you're trying to code this, what would you be doing? We've learned about functions, right? So what's the whole idea? What's the whole idea behind a function?
You have the input being transformed somehow into
Correct.
having output.
Okay, so how many outputs do we have in C functions? Six? Two? No. The first function is called, that you've written is called int main, right? You have some sort of input and then you return 0, right? So how many functions is that function returning? Infinity? 6? 2? 1, right? One variable, some sort of integer. And you see that all of the other ones, it's the same thing. They all return 1, correct? How many outputs does your full adder have? 2, correct? Is 2 equal to 1? Well, you guys are more awake than that, right? Is 2 equal to 1? There you go. So, if I can only return one function, a value in a function, but I have two values I want to return, what do I need to do? Might be cheating a little bit because I haven't quite taught you how to do it yet. See how many of you have actually, how many of you have taken C++? Okay, so like 3 or 4 of you. What would you do in this situation? Bingo. We're going to learn about pointers now. So, a pointer is used to indicate whether the value of a variable is located in memory, not the value of the variable. So, a pointer is used to indicate where the value of the variable is in the memory, not the value of the variable. So, if I give you an address, right? Give you Anderson 235, right? That is where ELE 385 is located, correct? That is not Professor Morrison, right? So the value of the variable is who teaches the class, Dr. Morrison. And I say, tell me where 385 is, and I say, Dr. Morrison. Is that going to make much sense, right? That's the common mistake in C and C++ coding. So I've included an XKCD comic here. So basically a segmentation fault is when you improperly allocate memory. And it says, and the computer starts talking to the code, says, okay, human, huh? Before you hit compile, listen up. You know that feeling when you're falling asleep and you imagine yourself walking or something and then you misstep, stumble, and you jolt awake? Yeah? That's what a seg fault feels like. Double check your damn pointers, okay? So we're going to learn a lot about checking pointers, making sure you allocate memory properly, free memory properly, and doing that in code here. Okay, so I have a little spiel about what I've just said, memory. We're going to talk about cache hierarchy and making sure that you properly allocate your pointers. Now, have you ever left your computer open for about a day and it's suddenly running really, really slow? Why do you think that is? Misallocated pointers. The pointers, so basically the pointer is saying, that has that much, I'm allocating this memory point, right? And then you point to somebody else in class, right? Okay, Colin, I want you to point to somebody, just point to anybody random. Somebody else. Any other human on the planet besides him, who I'm pointing at. Literally any other person but him. Yeah, there you go. Very quick one. Yes, I know. Literally any other. There you go. All right. So can we do tasks now? Because we're being held up. Right. Now you keep pointing. So if I'm the operating system, I'll ask you to do a task. Okay. Now I'm allocating you a pointer. I'll point to somebody in class. Right. You point to somebody in class. You point to somebody in class. You point to somebody in class. Now, if I'm not properly, what the operating system should be doing, it should be going back to, hey, you don't have to point anymore, you don't have to point anymore, you don't have to point anymore, you don't have to point anymore.
if I'm poorly coded, guess what? They're all doing this, and after a while, the overwhelming majority of the class is pointing at somebody, and you can't take notes, you can't write everything down, you're not doing your normal work, right? That's what they're talking about here, and that's why the operating system would have to, if all but 5 of you would have to like, are you pointing at somebody? Are you pointing at somebody? Are you pointing at somebody? You're not? Oh, good. All right, I need you to do something for me. If literally everybody else is pointing, and you're like my one person, right? So that's why the computer tends to run slower after a long time.
So we're going to learn how to avoid that. So pointers are represented in C code using the following 2 characters. An ampersand, which indicates that you want the address of the variable, and a star, which are the contents of the address, or dereferenced, or value pointed to by.
Now what this means is, if I'm calling an ampersand, say I'm passing the function, I need to pass the address to the function. This is what's known as passing by reference. What this means is, I want to put an ampersand in front of that variable and put it in my function call. And then in the function, I have a pointer. And when I come by and I'll say, all right, star variable. Now it says, go to that address, give me the value, and we're going to perform some sort of operation on it. Now, in order to do that, when you change the variable pointer with a pointer, that means you're changing the copy in memory. And I'll show you examples here in a second of what I mean by that. So if I'm calling a function, the function call would be int foo int star a, right? And then in the function, I would say star a equals 5, return star a plus 6 or something like that. Right, so no matter what is passed to A is going to be changed to 5. Now by dereferencing it here, I'm actually changing the copy in the memory that's called by the calling function, right? The function that calls it is going to call it like so. This will call foo ampersand A. That means send the address. So if my function tells students where the classes are, right, I would be saying ampersand class 235 indicates, ampersand ELE 385 becomes Anderson 235, right? And then what happens is once you come in here, you have a star, and then you get the value of the course, right? That's the difference. So I'm going to show you some coding examples here. So pointers.c. All right, so in my main, I initiate 2 values. Here I have int x and int y. Those are 2 integers. And then I have int star p1, int star p2. Those are pointers to integers. Declares 2 pointers to integers p1 and p2. So first thing I do is I say x equals -100, y equals 200, right? And then I have this p1 equals ampersand x and p2 equals ampersand y. So here's what this means. I have 2 values and 2 pointers. I give an actual value to the actual integer, to these integers in memory, and I have pointers indicating what they are. So we've learned briefly about registers, right? We'll go into that in a lot more detail in section 5. But the actual register holds a pointer telling me where in memory. It's to say, hey, these are going to tell you where something in memory is, right? And then when I say p1 equals ampersand x, it says, since this is an address, p1, right? This means p1 is equal to the address of x, because that's why the ampersand is. Give me the address.
P2 is equal to the address of Y. Does that make sense? This is something that many people get confused. If you work, I would highly recommend working through this coding example before you start doing your coding project that's due on October 4th. Okay, so let's predict our output. So here, how do we actually call these? So we have fprintf. I'm going to zoom in a little bit here so you can see all the code. All right, is that better? Those of you in the back? All right, so my first version of fprintf, initialized values. So I say std out integer values using x and y, %d, x and y. And then integer x and y using star p1 and star p2, %d. Now I have my comma like before, right? I have star p1 and star p2. What does this mean? I'm sorry, what? No. What's the other? It's the other thing. That's why I asked. Make a mistake and then learn. Not the address. So P1 is the address, right? What is from the TGO? What does star mean? Dereference. Give me the contents, right? So go to the. So when I say star, a P1, right? I know that this is a little confusing. That's why it's worth working through. Right? So when I initialize a pointer, I say star, right? Ampersand means give me the address and assign it to this pointer. And then here, dereference the address and give me the value. That make sense? Okay, good. If it doesn't, please put your hand up. This is many a computer scientist, computer engineer, and electrical engineer has been left at this concept. So if you don't get it, please ask questions. So what is this actually going to print out?
Negative 100 and 200.
And then what's this next line going to print out? Negative 100 and 200. Very good. It should be what it prints out. All right. So this next line of code, I changed 17. It should read 300 there. P1 star P1 equals 300. What does that line of code mean? Okay, so the value that P1 is pointing to is changed. What value is P1 pointing to? X, right? So here what I have is I've said the value of P1, but P1's still a pointer, right? So so I'm a pointer to you, right? And you're initially assigned 100, and they come by, the person that you're pointing to is now 300. I go to you, say, you're 300 now. I'm still pointing at you, right? So that's the way pointers work. So here's what's going to happen. After P1 equals 300, and we can cheat a little bit by going down to the printout. And you can see that we've replaced, after star P1 equals 300, that using P1 and P2 prints out 300 and 200 instead of 100 and 200. And then if I just fprintf x and y, it will do the same thing. So here it says star P1, P2, x and y. So now this is 300 and 200, 300 and 200, right? So now, okay, any questions on that before I move on to the next one? So this is where things start getting a little tricky, just as long as you follow it. So next line of code is P1 equals P2. No stars, no ampersands. What does that mean? Yes, exactly right. They are now both pointing to the same place. Specifically, P1 is now pointing to the same place that P2 is. So what was P2 pointing at? 200, right? And what's the variable that P2 was pointing at? 1. So what is P1 now pointing at? 1. Bingo. Right? So let's go to our printout. Again, we do the same thing where we're looking at x and y, P1 and P2. And guess what? Here's our result here. This first line is printing out X and Y, so it's printing out 300 then 200 like we did before. But then the second line says print out P1 and P2, and now they're both printing out 200 because they're now both pointing at Y. Right. So then 2 more examples, and then we'll be through this. So now P2 equals ampersand X. So what does that mean now? Pointing to the address of X. So what do you think is going to happen here? So you know you're going to have 300 and 200, and we say it's going to be 300 and, oh sorry, P2 is pointing at X, so that's 200, yeah, and P1 is pointing at Y. So this should be 200 and 300. Right? So now it's flipped, so we've now switched them. And as we predicted, it is switched. Yes?
Can you scroll back up?
Yeah, sure.
So since in the line before P2 equals ampersand X, would P1 not equal ampersand X now?
That is a very good question. So what the previous line, what the question is, P1 is now P1 equals P2. So this now we're going down to the architecture, what's physically going on. So P1 and P2 have 2 registers that hold the actual numerical value of the base pointer in memory. So when I say P2 is equal to P1, I have a number in the register corresponding to P2, and I have a number corresponding to the register in P1. So now I've taken that number in P2 and put it in P1. So now I have 2 copies of that number, which is why they're both pointing. So when I get to the next line, I've now found the address of X, which is not in either of these 2, and I put it in that previous P2 value. So now P1 has that other first number, and P2 has the new number corresponding to X. Does that make sense? So to draw it out, short version, what happened here is I had a register, let's say X is at 5, maybe we can make it 8 for consistency for base addressing, and let's say Y is at 16, right? And then I did P1 equals P2. That overwrites this and makes this now, let me choose a better color. So this is now, so this was 8 and this was 16. This line of code takes this number corresponding to the address, overwrites it, and then turns that into 16, right? And then this line of code finds the value of X, which is 8. So now we're here. Now, the question is, that should go away because it's not a pointer, because the pointer is the physical value of the address in memory in the registers. So that's why it's not going to follow on after that. So it's a good question, though. Any other questions? Yes.
What does printing out just P1 do?
That's another very good question. What do you think it does? Well, let's go back to what I was just talking about. There's everything in MIPS is 32 bits, right? And the register, the pointer, is a location in memory, and it's an integer corresponding to a location in the memory, right? So if I print this out, it's just going to print out some numerical value corresponding to memory. So usually it's going to be a very large number. So if you're expecting 200 and 300 and you take the star out, first of all, your compiler will give you a warning saying, hey, you haven't dereferenced your pointer. It'll be more technical, but that's what it's trying to tell you. And then you get out and you get, instead of 200, you'll get 1610, but something weird like that, right? That is what will physically happen. Does that make sense? That's what's physically going on inside the computer? Did I answer your question? All right, good. Okay, so last but certainly not least, instead of P1 equals P2, we have star P1 equals star P2. What is that doing?
Contents of the pointers equal.
Bingo. Dereferencing P2, So it gives me the contents, and then goes to P1, dereferences P1 here, updates it there. So what was the value of P2 pointing to? X, which is 200. So what's going to be printed out here? So that's all going to be 200, right? Because this means it's going to dereference. So this is actually equivalent to X equals Y, right? It's logically equivalent. It is physically equivalent. And then when we go here, that's precisely what happened. Wow, it's 10:42 already. Oh, wow. Okay, so I want to go over one last thing, and then we will... no, we'll just start with passing by value and passing by reference on Thursday. Okay, so everybody has all of their Section 1 and Section 2 assignments back. So at this point, you should understand Section 1, performance, Amdahl's law, computer architecture, computer organization, digital system, all that stuff, right? Everybody understands that? Okay, good. All right, your assignment is TGOs 3.1 through 3.9, and I believe you had 1 or 2 example questions. Example 3.1. Hey, you are dismissed.